Hi, Assalamualaikum. Our group will present about conduction graphical analysis on heat transfer, an assignment for subject BMMH3553 heat transfer. So, before we start, let me introduce my group member, starting with Muhammad AMIR bin Muhammad SHUKRI, MUHSIN AMILI bin NOOR, RUSHAN anak lelaki RANGANATHAN, and me, Muhammad AIMAN bin RAZAK. So let's start our presentation with theory. So heat sinks are one of the most common forms of thermal management in technology, machinery, and even in natural systems. Heat sink also a component that increases the heat flow away from a device. It accomplishes this task by increasing the device working surface area and the amount of low temperature fluid that moves across its enlarged surface area. So, how does a heat sink work? A heat sink works by moving heat away from a critical component. Nearly all heat sinks accomplish this task in four basic steps. First is the source that generates heat. So it's basically any system that creates heat and requires the removal of said heat to function correctly, such as solar, nuclear, chemical, and etc. Second is heat transfer away from the source. In direct heat sink contact application, heat moves into the heat sink and away from the source by natural conduction. The heat sink material's thermal conductivity directly impacts this process, and then heat will distribute throughout the heat sink. This step happens by a natural conduction moving across the thermal gradient from high temperature to a low temperature environment. And lastly, heat will move away from the heat sinks. So this process relies on the heat sink's temperature gradient and its working fluid. The working fluid passes across the surface of the warm heat sink and utilizes thermal diffusion and convection to remove heat away from the surface and into the environment and to the ambient environment. That's all from me. Thank you.
Hi and Assalamualaikum. I am Muhammad AMIR bin Muhammad SHUKRI. Nama matrik B092010491. So my part we explain about active heat sink versus passive heat sink. Heat sink are most commonly utilized in active, passive or hybrid configuration. So for the first is active heat sink. It utilizes forced air to increase fluid flow across the hot area. Forced air is most commonly generated by a fan, blower, or even movement of the entire object. An example of a fan producing forced air across a heat sink is the fan in your personal computer turning on after your computer gets warm. The fan forces air across the heat sink, which allows more unheated air to move across the heat sink surface, thus increasing the total thermal gradient across the heat sink system and allowing more heat to exit the overall system. For the second is passive heat sink. It relies on natural convection, meaning the buoyancy of hot air alone causes the airflow generated across the heatsink system. The benefit of this type of heatsink is that they do not require secondary power or control system to remove heat from the system. However, passive heatsinks are less effective at transferring heat from a system than active heatsink. And lastly is hybrid heatsink. Some characteristics of passive and active heatsink are combined. These are less prevalent arrangements that rely on control system to cool the system according to temperature need. When the system operates at cooler level, the forced air source is inactive, only cooling the system passively. Once the source reaches higher temperature, the active cooling mechanism engages to increase the cooling capacity of the system. So next is objective. First is to determine the temperature feel in a body and how the temperature within the portion of the body heat sink. Second is the analysis of heat sink dissipation across the body and in the environment. And third, lastly, to identify the design configuration of heat sink, therefore optimum for given condition. That's all from me. Thank you.
Assalamualaikum. My name is MUHSIN AMILI. Today I'm going to talk about our heatsink design. We have three different designs. So for the material, we use aluminium. And we set the thermal conductivity of this three design is 247 watt per meter Kelvin. And the thermal coefficient is 0.000023 per degree Celsius. So for the first design, we designed this heatsink has the most fin among the three design. And the second design, we incorporate inverted Y fin into our design. And the third design, we take an extra step to design this fin the most unique among the three, which has similar design heatsink that used in the PC. So after we design all these three heatsink, we do a graphical analysis on these three heatsink to obtain the heat dissipation and heat flux for this design. That's all for me. Thank you and Assalamualaikum.
Hi, my name is RUSHAN. I'm from BMMH section 2. Okay, today we are going to do conduction graphical analysis on heat transfer. Okay, before that, we are going to look at the parameters for the analysis, which is the ambient temperature, which is from 28 degrees Celsius to 34 degrees Celsius. The fin base size for the heat sink, which is 44 mm, 40 mm times 40 mm. The convection coefficient, which is at 5.03. The average heat flux on the cold side, which is at 1500. The average temperature on the cold side, which is at 76.6. The average temperature on the hot side, which is at 97.3. Okay, before that, let me show you. We are going to do ANSYS steady state thermal analysis. We go to the left hand side. We click on the steady state thermal analysis. Okay, then you get it on the project schematic. You key in your engineering data, which is aluminum alloy. Then you import your geometry from your other CAD program, maybe using Design Modeler, Katia, SolidWorks, any sort of design software. Then you click on model and you go into the analysis page. Okay, here you can see the model. Okay, before going any further, I'm just going to show you the boundary conditions which need to be set up in order to get the desired results. Okay, for this analysis, we're going to go through heat flux, convection, cold side, and also hot side. Okay, heat flux is also known as the heat flux density or heat flow rate intensity. Okay, next we are going to go at the convection. Convection is the rate of heat transfer between solid surface and fluid per unit surface area per unit temperature difference. Okay, so this is the region for heat flux. This is a convection region, as you can see. Okay, this is your cold side and this is your hot side. Okay, once all these conditions are set up, then only you will run your analysis, and through this analysis we'll be able to see the plots of temperature difference and also the total heat flux, and in other cases you can also see the directional coefficient, directional heat flux. Okay, So once you have done setting up all your boundary conditions, then you will be able to run the analysis. And after this, I'll show you the boundary conditions for the 3 designs that my group has designed, and also we have done a thermal analysis on it by using NCs. Okay, in that you will be able to see the heat flux, convection, and also the total heat flux and directional heat flux. This data will later be compared, and also we are able to see the direction of heat flow from the hot region to the colder region. Hi, my name is Rushan. I'm for BMMH section 2. Today for heat transfer, we are going to do graphical analysis on a heat sink. Okay, the program that I'm choosing to do the graphical analysis is NCs. Okay, first we are going to check on the engineering data. This is to set the material for our analysis of the heatsink. Okay, this to be precise, this is the material that we're going to set for our heatsink. Click on edit, go to engineering data sources. You're going to choose materials. So let us see. Okay, we are going to choose general materials, and we are going to go for aluminum alloy. You have to click on this button here, which is add to A2. A2 is the engineering data. Okay, once you have clicked this, your data shall appear here. You can delete any unwanted materials. Okay, next you have to import your geometry. Maybe you have drawn it using SolidWorks, Design Modeler, or any other software. So we are going to import it to geometry. Okay, next we are going to go to model. So once you have imported it to the geometry, you will receive a tick on the right hand side. Next we go to model. So it shows upstream data needs to be reread. Would you like to reread the upstream data? Yes, I would like to reread the upstream data. Okay, so this is our geometry of a heat sink. Our heat sink is full of fins which are uniformly placed. Okay, next let us look at the geometry. Once you're in geometry, you click on the model and then go to as material, and below material is assignment. So you have to be sure that your model is aluminum, since you want to run an analysis using aluminum alloy, and most heat sinks are made of aluminum alloy and many other different materials such as stainless steel and so on. Okay, we click on aluminum alloy. Okay, so next we go to steady state thermal. So we are going to do a steady state because it is used to determine the steady state temperature distribution and heat flow. So these are the 2 things that we are going to look at today. Next, you go to initial temperature to set the temperature. Okay, I'm going to set it at 34 degrees since the range is between 28 to around 34 degrees. And make sure it's in Celsius. Okay, next you go to heat flux. Okay, this is your heat flux. Heat flux is also known as the heat flow density or heat flow rate intensity. When you think about heat flow rate, okay, so heatsink is placed on a heated component, for example, maybe a resistor or transistor or some sort of component, semiconductor component, and the heat goes from down to up. And in simple terms, it's from hot to cold. Okay, you set your heat flux at 1500. Then you go to convection. Okay, since convection in heat flow, heat is transferred via convection, so you have to select phases and select each body where you feel that convection occurs and also heat flow is transferred. Okay, then you set on the cold side, which is at the top, which is at around 76.6 degrees Celsius, and the hot side, which is around 97.3. Okay, once all the boundary condition is set up, you have to solve the solver. You click on that and you'll see the solver solving. Okay, once each of the tree below the solution, which is at A6, it has turned into green. You can check. So this is the temperature. Okay, here we are able to look at the temperature distribution, which is from 97.3 degrees Celsius, which is the max temperature below, and towards the top is around 76.6 degrees Celsius. Okay, to get a more cleaner look of the temperature distribution, you can click on section plane and then size the model. Okay, once your model is sized, you are able to see even clearer. Okay, how does your temperature distribution look like? You see, at the below it is more hot, and towards the top it's getting colder, and you can see the range. So below it's around 97.3, and when it goes up, okay, you're able to see around 90.931, 89.338, 82.969, and also 76.6, which is the minimum temperature for the model. Okay, now let us look at the total heat flux. Okay, for the total heat flux, we are able to see the maximum and minimum value. The maximum temperature heat flux at the top is around 2.8856, and below it's around 3972.5, which is the minimum. So heat flow intensity at the top is lesser than the heat flow at the bottom. Okay, next we are also able to see the directional heat flux for the X, which is at 1.5963, which is at the max, and also at negative 564 times 10 to the power of 5 minimum. And then at the Y direction, you are able to see the maximum heat flow and also the minimum. The maximum is at 31569, which is at the site, towards the sides, and towards the top there's a minimal directional heat flux. And then you're also able to see for the Z-axis. So there is minimal heat flux toward around the Z-axis. Okay, so far this is how you set the boundary condition, and this is how you analyze this is how you analyze your temperature and your total heat flux. Okay, now let us look at the second design which we have done as static thermal analysis. Okay, we are going to look at the engineering data. Okay, we have already added the engineering data, which is aluminum alloy. The geometry is complete and there's a tick at the side. Next is the model. Once we have clicked on the model, we click on edit, and you have received you have went into the simulation screen. Okay, you check at the initial temperature, which is at 34 degrees, the convection, which is at 5.03, the heat flux, which is at 1500, the temperature at the cool side is around 76.6, temperature at hot side is around 97.3. Okay, once your simulation is done, you will see a tick under the simulation tree. The temperature, the total heat flux, the directional heat flux in X, Y, and Z. Okay, so here you can notice the temperature distribution, which goes from 97.3, which is the max temperature, up to the top side, which is around 76.6. You can see that variance in the temperature distribution. Okay, this can also be caused by the less number of fins, and there is a lot of airways throughout the fins. So there's the temperature distribution contour is even more clearer. Next, we'll look at the total heat flux. Okay, here we are able to notice the total heat flux for where there is minimal heat flow, and also at certain regions you are able to notice here there is up to 7329 and around the range of 48,000 and 57,000, which we can notice at both areas here. And between two fins, there's a very large difference, as you can notice here. Okay, next, let us look at the directional heat flux at X. Here you can see there is around -2 to 5.9, and also at certain areas, when you look closely, there's around maximum heat flux which is at 15,906. Well, for the y-axis, you are able to see the total directional heat flux, which is similar to the total heat flux. There is a wide range of temperatures ranging from 7,260 to 10,071. Okay, so next, in the Z direction also, you're able to see a wide range of temperature distribution. This temperature distribution may be caused by the fluid in between the heat sinks, which is air, and also the shape of the heat sink, which distributes temperature more evenly, okay, since there is more space in between them. And you're also able to see certain areas where there is a maximum heat flow, and certain areas with minimal heat flow. Okay, if you want to check it in more detail, you can also size, and you are able to see more clearly, and you're able to see the contours more clearly from the bottom part to the top part on how the heat flux is distributed. Okay, now let us look at the third and last and final design. Okay, so once again, you choose your engineering data, your geometry, and now let us go into model. Okay, before going to the model, the steady state, I would like to repeat, it is used to determine the steady state temperature distribution and also heat flow. That is what we are going to do a graphical analysis. By the means of graphical analysis is we are going to do a contour analysis on the design of the heatsink. Okay, this is the third design, which is an inverted Y heatsink. This heatsink can be located in CPUs and also in some of the electrical equipments. Okay, once again, let us look at the initial temperature, which is at 28. Let me change it to make it uniform at 34 degrees Celsius. Okay, next is the cold side. The temperature of the hot side, which is at 97.3, and the cold side is 76.6 degrees Celsius. This is the convection, since heat is transferred via convection, and this is the body where the convection occurs in a heatsink. And this convection occurs from the heatsink and out towards the environment. Okay, next is the heat flux, which is at 1500, and the convection coefficient is at 5.03. Okay, from that, now let us solve it. Okay, once your solution tree shows a green tick, that means all your equation is solved. Okay, now let us look at the temperature distribution. Okay, for this heatsink, we are able to see the temperature distribution, which is from the max, which is at 97.3, and the minimum temperature distribution, which is at 76.6. Okay, when you look at the distribution of the temperature, you are able to see the contours which go from the hotter region, which is at 97.3, towards 95, 92.7, towards 90.4, towards 88.1, and all the way to 76.6 degrees Celsius, which is the minimum temperature. Okay, now let us look at the heat flux. Okay, the heat flux flows intensively at the bottom, which is at 1104.6. There's minimal heat flux at the bottom, and also the maximum value of heat flux is at 5.447 to the power of 5, which is towards the top. And you're able to see the contours towards the top, which are in various colors. It ranges from a light green to a lighter green, yellowish, orange, and also red. And these contours can be used to be compared with the legend on the left hand side. Okay, after looking at this, let us look at the directional heat flux. The directional heat flux at X, we are able to see the directional heat flux, which is at negative 68958 at the bottom, towards the top, which is around negative 7165.7, 8282.4. Okay, and there is certain regions which has a higher heat flux rate, which is at 70,075. For example, at this region here. Okay, so at this region here, we are able to see the maximum heat flux, which is at 70,075. And you are able to also see the contours on how it is ranging from, which is at 82.82.4 up to 70,075. Okay, this can be also noticed on the other side, where there is a wide range of temperature, a wide range of heat flux, which is at 8,282 to up to 68,958. Okay, now let us look at the y direction of heat flux. Okay, it shows the minimal temperature, minimal heat flux at the bottom, and towards the top, it has a maximum value of 5.449. And the heat flux at Z, it shows a minimum value of negative 68958 to a maximum value of 70,075. Okay, so this is all our boundary conditions on the cold side, the hot side, convection, and also the heat flux. And this, by using these boundary conditions, we have created our energy. Based on these boundary conditions, we have created our analysis.
The conclusion, what we learned from this assignment is that the key factor should be considered in heatsink design: thermal resistance, a material, fin configuration, fin size and shape, fin efficiency, heatsink attachment method, and thermal interface material. And second, we learn in this assignment is a heatsink maintains and controls thermal energy by transferring heat from a device element to the surrounding. And the third, effective dissipation of thermal energy by a heatsink is largely depend on its design. And lastly, what we learn in this assignment is a different layout of heatsink. Consequently, from a different heat flux between fin base, the temperature field for both base and fins are symmetric because of contact heat flux. The increase in the number of fin or convection enhance the heat dissipation of heat sinks. That's all for me. Thank you and Assalamualaikum.